Greetings to everyone. So, this is Kavita Kadam. Today, we are going to start with the topic coordination chemistry from class 12th. And in this particular video, we are going to start with the topic, and it will take few more lectures, I think, to finish up this. Let's begin with this important topic. Most of the times, I've found that children are finding slight difficulty in understanding the concepts of this coordination compounds. So, let's begin with the definition. I think we can see the screen. So what are coordination compounds? This name coordination is a little first time you people are hearing this name. So the word coordination means it talks about a new word called as complex. So the compounds in which the central metal atom or ion is linked to a number of ions or neutral molecules by coordinate bonds. They are also called as complexes. So the most important point over here is coordination compounds are actually so called because they are having coordinate bonds, and everyone knows what is a coordinate bond. For example, if I talk for simple example like NH3, which is a Lewis base because it has lone pair of electrons, and when it reacts with proton like H plus, which is a Lewis acid because it is deficient of electrons. So when these two species come together, they will definitely react. Okay, so here this NH3 is going to give the lone pair of electrons to H plus. It is going to donate it, and the donor is ammonia and the acceptor is H plus. So the new complex which is going to be formed will be NH3, and we can show an arrow going like this, and we can write here H. So this complete species will be called as NH4 plus basically. So what we can see here is there is a coordinate bond, the one which has been shown by the arrow, right? So this is a coordination bond. So coordination bond basically is going to be a bond which is formed by the donation of an electron pair from a Lewis base to an acceptor, that is Lewis acid. So basically in exam you can just write coordination compounds are those which contain essentially coordinate bond oblique bond. So they can be one or they can be more than one bond present. Now the most important point here is when we talk in coordination, there will be definitely a central metal atom or ion which will be linked to a number of ions which can be of course negatively charged. For example, you can have Cl minus, or it can be positively charged, or you can have neutral molecules also like water for example, and they are all linked by coordinate bonds. So these coordination compounds, they are also known as complexes. So what we have learned here is in a coordination compound, the central metal atom or the ion will be connected or will be attached to a number of ions. So in class 12th, if we see the NCERT textbook, you will just find negatively charged ions which are used, or you can say neutral molecules are also there which are connected through coordinate bonds. So the most important point is that a coordinate compound does not lose its identity in the solution, whereas a double salt loses its identity in solution. So this, we should not get confused between a double salt and a complex salt or a coordinate compound. So I have used a word that is complex salt. Now complex salt is nothing but a coordination compound. So there are two important terms like a double salt, which is made up of two simple salts, and there is another term called as complex salt, which is a coordination compound. Now what is the difference? Essentially, if you see in coordination compounds, you are definitely going to have a coordinate bond, whereas in the double salt you will not, you may or may not have that, the coordinate bond. So now look at this, like for example, you have the first compound which we are giving you is K4FeCN6. So in this compound, what you see is that there is a central metal atom over here, like that is Fe. Okay, so inside the square bracket, so inside the square bracket I am writing iron, which is the transition metal, that means it belongs to the D block. It will be now called as central metal ion. Why is it called as ion? Is because its oxidation state over here is +2. So it is not an atom, it is an ion. So we are going to say that in this particular compound, the central metal ion is surrounded by 6 cyanide ligands, okay, 6 cyanide Lewis bases, which we are going to actually call ligands. Okay, so we're going to call it as ligand. So what is ligand? Basically, ligand is an electron pair donor, or it is a Lewis base, right? So now there are two ions over here. One is potassium ion and another one is this hexacyanoferrite ion. So if I write it, it's going to be like, I'll just add water in this potassium ferrocyanide. So the name of this compound is in the common, familiar words, we can call it as potassium ferrocyanide, right? But we will learn how to name it in the according to the IPAC nomenclature later on. But presently, just understand that a coordinate compound is made up of, a compound will be having definitely species. There will be a square bracket is compulsory over there, and 100% you need to have a central metal atom, or you need to have a central metal ion, which should be surrounded by ligands or Lewis bases. All right, and what can be the ligands? What kind of ligands are these? So these ligands are going to be ions, or they negatively charged ions, or positively charged ions, or they can be the neutral molecules. So presently in the complex which we are seeing here, FeCN6 is enclosed in the square bracket, and its overall charge is going to be -4. So this particular species which we are denoting here is actually this species is actually the one which is the coordinate entity, right? So now look, what we are doing is I just take K4FeCN6, that is potassium ferrocyanide, and I just add water to it. So what happens naturally, the cations, that is potassium cations, get separated and you get 4K plus ions. The hexacyanoferrite, that is FeCN6 -4, also gets separated. So that is they have they've just got separated. But have they lost their identity? Have they broken their coordinate bonds? No, they have not broken their coordinate bonds. So that is the point which is written over here. This is important for your exam. A coordinate compound does not lose its identity in solution. That means its bonds are not broken. Its coordinate bonds are still intact. Whereas if you add a double salt in water, or it loses its identity in solution. So like the most important example right now in front of you, which we can see, is the Mohr salt. Okay, so this is a Mohr salt, which you can see it is also called as FAS in short, that is ferrous ammonium sulfate, right? So this is a double salt. Naturally, why is it called double salt? Because it is made up of one salt, that is FeSO4, and another salt, that is NH4 twice SO4, that is ammonium sulfate. So this is double salt. Now when I put double salt in water, it will definitely break completely into its constituent ions. Okay, it will break completely into constituent ions. Whereas if a complex salt is added, or a coordination compound is added in water, it will not break completely into its constituents, right? And that means double salt has lost its identity. It has got completely separated. So what am I getting here? I'm getting iron, that is Fe2 plus aqueous. I'm getting sulfate, that is SO4 -2 aqueous. I'm getting NH4 plus, again I have to write aqueous, and water molecule 6, water of crystallization, they have all come out. So all the ions are ionizable in a double salt, whereas all the ions are not, they are not breaking down in a complex salt. So let's recap. What's a coordination compound? A compound which is essentially containing a central metal atom or ion surrounded by negatively charged ions or positively charged ions, or the neutral molecules, which are known as ligands, and connected by which bonds? Connected by the coordinate bonds. The question often asked in the practicals also is that what is the difference between the two addition compounds, double salt, and a coordination compound? So the difference is that when you add water in a double salt, it loses its identity, whereas if you add water in the coordination compound or a complex salt, it does not lose its identity, which means that it does not break completely. Now these two examples which I have mentioned in the slide over here, the first example of a coordination compound, that is potassium ferrocyanide, is can be given in the board exam by you, and also double salt like Moha salt also can be given in the exam. Now, once again, I'll give you one more example of a coordination compound. So here I have another coordination compound, that is, like for example, I have NiCO4. So this is a tetracarbonyl nickel. So in this, children, you can see that there is no cation or an anion, but this entire species itself is a neutral coordination compound. So basically the coordination compounds can be of three different types. I'll just give you an idea. So here, of course, we can have a cation and an anion. Now this cation can be a complex cation, and the anion can be a simple anion, right? Or it can be the other way around also. That means it means that the cation can be simple and the anion can be complex. Now, what is the example of this? We will see one by one. And the third category is the one in which there is no cation and no anion, whereas the whole molecule itself is a neutral molecule. Like this is the example of the third one is NiCO4. Now, let me give you the example of the first category where the cation is complex. What do you mean by complex? Which means that the cation is enclosed in the square bracket. So to understand essentially and identify the complex, you have to see symbolically the square bracket. So the example for this category is this one which I am writing right now. So see here. So here you can see that I have on the LHS, I have the cation which is written in the square bracket. So this is a complex cation, whereas the anion is outside. So it's on the right side. It's a simple one. It doesn't have any square bracket kind of thing. So this is the first category you will see in your textbook examples. Now the second category which just now we did was the one like K4FeCN6 or anything like that. So the same example I would write down K4FeCN6. So in this example, what did you see? You saw that the cation is a simple one, whereas the anion is a complex one because it's written in the square bracket. And the third category is the one which I have written here. That means the whole complex is written inside the square bracket. There is no cation or anion, but it's a neutral complex. So this is how we can give the examples of such complex compounds. Now let me just give you some brief idea about what is a central metal atom over here. So in the first example, you will see that whatever is inside the square bracket, you have to see the first metal which is written, that is the cobalt in this case. So cobalt is the central metal. Whether it is an ion or whether it is a metal atom, I have to check that. So for that, you will see the counter ion. That means the ions which are written outside the square brackets. It's very easy to identify the oxidation state of the ions which are written outside the square bracket. So the oxidation state of chlorine is -1. So definitely it is 3 chlorine. That is 3 chlorides. So 3 into -1 is -3. And therefore on the top of the square bracket, you must write +3 because +3 and -3 should give you the charge of 0 on this coordination compound because it's a neutral compound. Naturally, now when we talk about ammonia, that is NH3, it is a neutral molecule. So you have to remember certain points in this chapter, like ammonia is a neutral molecule, so the charge on ammonia is 0. So definitely cobalt will have a charge of +3. That means cobalt has lost 3 electrons in the during the formation of this complex. So what is cobalt? Cobalt is a central metal ion. What is ammonia? 6 ammonia molecules are nothing but the Lewis bases, or we can say they are the ligands. And what kind of ligands are they? Of course, they are neutral ligands because they do not have any charge. And what is a Cl minus? The Cl minus is nothing but a simple anion which is, which can be called as a counter ion. The second example, when we see this K4 FeCN6 over here, when you talk about the square bracket, here you will see that iron is the central metal ion. K4 means we have to write the charge of 4 plus, and FeCN6 the charge of -4. Cyanide is the ligand, that means it has a charge of -1. So Cn 6 times, so -6 into -6 into -1 is -6. So the charge on iron is +2. So somebody's bursting crackers. So now iron will have a charge of +2. That means it is a central metal ion surrounded by 6 cyanide ligands. Potassium is a counter ion, right? Now the third example. So here the nickel is the central metal. What is it? Whether it's an atom or an ion, let's check out. So the total charge on this complex is 0. Carbon monoxide is called as carbonyl. So now children, you have to remember certain names whichever we are having and in the textbook and important for your board examination. So these names I'll be writing over here, so please try to remember them. So carbonyl, so we are not calling carbon monoxide as carbon monoxide. We are not calling water as water. We are calling it as aqua. So the names of the ligands is going to slightly change. When you are making a complex compound, the names of the molecules will change. Like CO will be called as carbonyl, water will be called as aqua, ammonia, that is NH3, will be called as amine. Okay, so this is how we will address them. So what is this carbon monoxide? It's actually a neutral ligand, neutral molecule, so its charge is 0. So definitely it's very simple logic that nickel is also going to be a 0 charge. That means it is an atom, central metal atom. So we have not removed any electron from nickel at the moment. So I'm sure you've understood the concept of what is a coordination compound or a complex compound or a complex, let's say sometimes salt also we can call it. That means a compound in which a central metal atom or ion is surrounded by ligands, right? Connected by coordinate bonds. And what are ligands? Ligands are the electron pair donors. They can be positively charged, they can be negatively charged, they can be neutral. When you dissolve a coordination compound in water, what happens? So the answer is it simply dissociates into a cation and an ion, but the complex does not completely break down. That means whatever square bracket species is there, whatever complex species is there, or whatever coordination entity is there, it is not going to break down. So that was your brief introduction, and now we'll just discuss about the first important topic for you. This will be for hardly a question of 1 mark or 2 marks can be asked in the board examination from here. So children, the first scientist who studied about these coordination compound was Alfred Werner. So we must know the name Alfred Werner, and he had chosen 2 important compounds for his study. What did he do? Alfred Werner, basically he took a compound like COCl3. This was the compound which he took, and COCl3, that is cobalt trichloride, is already a very stable compound. And he took ammonia, which is also a very stable compound. So what did he do? He just thought, let's see what happens when I bring these 2 compounds together. Are they going to react or not, right? So are these stable compounds going to react? So what did he find? To his surprise, he found that yes, they do react. So these 2 compounds, when they react, you will get a formation of a complex compound or a coordination compound. So the compound which I wrote just now a short while ago, that is CONH3 let's say Cl3, this was the compound, let's say one of the compounds which he had prepared that time. So Alfred Werner, when he studied about these compounds, coordination compounds in great detail, he gave some points, he gave some theory, he gave some postulates. So let's understand what are these postulates. So Alfred Werner was the first scientist to give the idea about the structure of coordination compounds. And which compounds did he use for his study? We already discussed COCl3 and ammonia were the 2 compounds which he used for his study. The postulates, very, very important now. What are the postulates of Werner's theory? The first important point which he put forth was that every metal ion in the complex has 2 types of valencies. The first is primary valency and the second is secondary valency. All right. So what is this primary and the secondary valency? Let's understand. The primary valency is nothing but the oxidation state of the metal ion. and it is ionizable. Okay, so when we look at the example which is here, in this case we can see that this example I'm talking about. Focus here. So in this example, what will be the oxidation state of cobalt? Chlorine will be 3 into -1, that is -3. This entire complex entity will be +3. Ammonia is a neutral molecule, so 0 is the charge, and definitely cobalt will have a charge of +3. I'm sure you've understood this point. Once again, chloride is a negatively charged ligand. Sorry, not ligand, it's a negatively charged ion. So Cl is -1 into 3 is -3. This square bracket species, which is called as coordination entity. So this square bracket species, which is called as coordination entity, has a charge of +3. And when you solve this complete thing, you get the charge on cobalt as +3. So what is this +3? This +3 is the primary valency of cobalt. You remember this because this is going to be asked in the board exam. Okay. So how to calculate the primary valency? It's very simple. It's nothing but the oxidation state which you calculate with your wisdom and with your intelligence and with your understanding. Okay. So cobalt is going to be +3. Right, it is ionizable, definitely, because you know who's satisfying the +3 charge of cobalt, who's that species, which is that species which is satisfying the charge of cobalt +3? Naturally, it is chloride, which is -3, right? So this is +3 and this is -3. So when you put this compound in water, isn't the Cl- getting dissociated? Definitely it's getting dissociated. So you will say that the primary valency refers to the oxidation state, and it's definitely completely 100% ionizable. Now what is the secondary valency? The secondary valency is nothing but the coordination number of the metal ion, and it is non-ionizable. This is very important. Now when you look at cobalt, how many ligands have surrounded it? How many coordinate bonds are there around it? So ammonia is 6 times, it's written over here. So cobalt actually is making 6 bonds with ammonia, so which I'll just draw and show you. Look at this. Look at this, children. So you can see I'm going to draw arrows because it's a coordinate bond. The bond has to come from donor to acceptor. So who's the acceptor? Cobalt is the acceptor. Who's the donor? It is ammonia is the donor. How many ammonia? 6 ammonia. Let's draw it. So I'm drawing it. You can see here, and I'm drawing it in a very proper way, showing that nitrogen is the one which is donating the electrons. Okay, I should draw it in such a way that the donor atom is attached with the tail of the arrow. And now just put the square bracket. Put the square bracket. And what was the charge on that square bracket did we write? What charge did we write? We drew the charge of +3. Let's just get rid of this complete thing first. So we have to write the charge of +3. And what was outside the square bracket? It was Cl3. Okay, so children, this is the way you're going to draw in the board exam. Now, what is the secondary valency? What am I referring to? The secondary valency is the total number of ligands actually, which are attached to the central metal atom or ion. So how many ligands are you having? How many coordinate bonds are you having around the cobalt? 6, right? You're having 6 coordinate bonds. This is the first one, the second one, the third one. Let me just show you properly. So this is the first one, the second one, the third one, the fourth one, the fifth one, and the sixth one. So in this manner, you have got total 6 coordinate bonds. So that is a coordination number, and it is non-ionizable naturally, because when I put this entire complex in water, what will happen if I put this entire complex in water? This coordination entity is never going to break. That means जो दरवाजा है, that means the door. I call it as a door. The square bracket, I call it as a door. This is never going to open. It's going to remain intact. Only by chemical reaction is that door going to open. Okay. So when I put this in water, which I just show it in the exam like this, H2O. So what will happen? This entire thing, that is CONH3 6 3 plus, will break down. I mean, it will just dissociate, and I can just write AQ over here because it's surrounded by water. Plus the 3Cl minus will be separated out like this. So in this manner, the coordinate, they are non-ionizable. That means these bonds are never going to break. And the last point, which is extremely important for us to understand, is that the primary valency is non-directional, which means that it is not going to have any direction. It is wherever the central metal atom is going to go, there the primary valency is also going to go anywhere. That means it's not having any on the axis. You cannot say that it's on x axis or y axis or z axis, or it is having some angle, it is having some orientation. So are these primary valencies having any orientation in the space? The answer is a big no. So the primary valency is non-directional because it is just held by ionic bonds. Whereas the secondary valencies, they are having directional properties. That means they will be having some orientation, they'll be having some hybridization concept will come here, and they will be helping us to predict the geometry of the compound. Okay, so they will help us to predict the geometry. So we'll just a quick recap at postulates of Werner's theory. Every central metal atom, every central ion, or of course ion, because if it's a metal atom, it will not have its primary valency in that. Of course it can have. So we can write here every central metal atom or ion in the complex has two types of valencies, primary and secondary. The primary valency is nothing but the oxidation state. It is completely ionizable when added to water. The secondary valency refers to the coordination number of the metal ion, and it is non-ionizable. What is coordination number? It is the total number of ligands directly connected to the central metal ion. The primary valency is non-directional. That means it is not having any particular angle, oblique orientation. Whereas the secondary valency has directional properties. It has got some angle, it has got orientation due to the hybridization on the central metal atom or ion. So which valency helps us to predict the geometry or the shape of a complex? So the answer is definitely the secondary valency. So I'm sure you have understood this complex, children. Please work hard. Coordination chemistry is requiring a lot of hard work and sincerity also. Now I'll just give you the last example, and with that we'll stop here and continue the next session. So the example which I would be taking right now, so I'll take this example which is quite famous, CuSO4.5H2O. Okay, so this is copper sulfate .5H2O, which is called as blue vitriol, and actually this is a complex compound. So when you draw the structure of this compound, it would be CuH2O4 times, and you have the sulfate outside the square bracket, and you have one water molecule outside the square bracket. So children, this is a coordination compound, and what is the central metal atom or ion over here? Copper is the central metal. Whether it's an ion or whether it's an atom, let's understand, let's calculate. So the charge on sulfate is -2. The charge on this coordination entity will be +2. The charge on water is 0. So 4 into 0 is 0. So the charge on copper should be +2 naturally, because you want to get this +2. The charge overall has to be +2, right? So what should be the charge on copper? It has to be +2. So it is a central metal ion. What are the ligands here? Water is a ligand. It is neutral ligand because it does not have any charge. So let's write it's a neutral ligand. How many bonds are we making? Copper is making with water. So naturally it is 4, because water can just make one bond. So it is the coordination number of copper +2 is 4. Primary valency of copper primary valency of copper here is +2. So what is +2? +2 is the primary valency, because it's the oxidation state. Okay, what is the secondary valency of copper +2? How many bonds it's making with water? So 4 bonds. What is the coordination number of copper +2? 4. So 4 is the secondary valency. It's having a directional character. Okay, and I think that's all. And what is the coordination entity in this case? So whatever is inside the square bracket, it's called as the coordination entity. So this species which I am circling right now, look at this particular thing. This is the coordination entity. Okay, and what is the counter ion? The ion which is outside the square bracket, which can be positive or negative, it's called as a counter ion. So presently this is the counter ion. Sulfate is the counter ion. Okay, so I'm sure you've understood this logic, children. So see you in the next class, and we will be beginning with the next topic, that is, I think they'll show you ligands. Thank you so much, and please work hard. And you may post your comments down in case you find that certain topics need to be discussed. We will be doing that. So till then, you all have to take care and please work hard. Thank you.